Hello everyone, I'm Rohit here and I am the author of this book, Decoding Gravity, Time and Causality, which is a book which describes a new theory of everything, dynamic general relativity. So what we are going to discuss today in this video is what are the predictions of DGR and how to test them. So an ideal theory of everything, or for that matter, for any theory, scientific theory, should have some predictions and we should be able to test them. And most of the theories which we are currently having as candidates for theory of quantum gravity and potential theory of everything, most of them don't have any real predictions, and also they don't there's no way, even if there are some predictions, there's very little you can do because the predictions are way they need a lot of energy, so they're beyond our testable range. So this is not the case with dynamic general relativity. So the dynamic general relativity, as I have mentioned in my first introductory video and also subsequently, that there are multiple predictions of DGR. And so DGR is in a way much different. Now, here I would assume that you have some idea about DGR. So if you have not seen the first video, that is the introductory video, and for subsequently a couple of other videos like how time is different in DGR, why we have some problems in understanding of time, and also how gravity is slightly different in DGR, and how we don't know general relativity well yet. So if you have not seen all these videos, please go and see them first before indulging into this video, because in this video I'm going to assume that you have a bit of idea about what DGR is. Anyhow, I'll not be able to give the entire whatever contents of the book in these videos. So it is I don't know whether you will be able to understand all what I'm saying, because a lot of it is given in shortcut basically. So to understand it fully, you will have to still read the book. But I'll just try to make it quick and make it understandable. So what are the predictions of DGR? Well, basically, yeah, so this is the book which I'm talking about. This is the Decoding Gravity, Time and Causality. Okay. So first of all, there's something called as a tunnel vision, basically. So every what I would want to put it is this way, that every theory, according to me, is an example of tunnel vision. That is, you have a horse actually, and you have two there are some plates like that on the horse, so that the horse cannot move from you cannot see this part and this part, and only can see the front part. So like that, if you see through a small pipe, then you can see only a small part of the picture. You cannot see the whole picture. So that's something called as a tunnel vision. There's an analogy basically. So basically, elephant analogy you can use to understand what I'm trying to say. So every theory, according to me, is having tunnel vision. Means what? Let's say that elephant is the theory of everything, or the potential. We assume that there is a theory of everything, and this is the elephant. So every physics theory of ours will see a very small part of the elephant. So it will either see only the trunk, and you assume that the whole theory is basically the elephant is like a trunk, like a snake, and some another theory will come which will see only the foot, and it will assume so they will say that yes, the elephant is like a pillar, or they will focus only on the fans, and they will come to the conclusion that the elephant is like a fan. So like that, every theory focuses on one part of the reality. So it doesn't focus on the whole of the reality. That is what I assume, and that is what I believe, that let's say Newtonian mechanics, we know that Newtonian mechanics worked very well on the surface of the earth, on the laboratories and all, and maybe even on the satellites, and maybe for all the other planets within the solar system. But it did not work well to predict the Mercury orbit of Mercury, and there were quite a few other things which it could not predict. So basically, it was looking at a smaller part of the whole picture. And then Einstein's theory of relativity probably has a much more broader outlook, so it can see, and it has the predictive capability of Einstein's general theory of relativity is much more than Newtonian gravity. So, but even then, Einstein in gravity was not able to predict gravity properly at at very large, that is galaxy scale and above galaxy cluster scale. So we needed dark matter for that also. So basically, that's what. So the range of the theory is limited, and of course, general relativity cannot give any predictions about how the photon is, or what is the space-time curvature around the photon, or what is the space-time curvature within the black hole. And so basically it has some limitations. So it is seeing one part of the whole elephant. It's not seeing the whole elephant. Like that, all theories are viewing one part of the elephant and not capable of viewing the other part of the elephant. So that analogy is pretty good. So in that sense, I think the DGR can give predictions and can see basically almost the entire elephant. But this would basically be arrogance if I say that. So the best thing would be, we don't know yet that that DGR is still in a bit of infancy. But this is the beauty of DGR, that it can provide predictions all throughout the range, right from very large to very minute, tiny quantum scales, and it can give pretty good predictions. So there are some predictions. So we come to Newtonian gravity and DGR. What are the predictions of Newtonian gravity which DGR can very well, which go very well with DGR? Instantaneous transmission of gravity. So this is a very controversial prediction of Newtonian gravity, which most of the people were thinking that what is it? What rubbish are you talking about? Now DGR is not actually saying it is instantaneous transfer, but it's saying that the transfer of gravity related information, that is the time resetting waves which start from the earth and go towards the sun, or they start from the sun and go towards the earth. They go much faster than speed of light. And why that happens is described in the first video, basically, so introductory video. But I will go in brief. Basically, every particle which makes the earth and the sun has a lot of destruction going on in their core. So each particle has a lot of destruction. So each particle not only has T is equal to 0 compartment, but they have millions, billions, trillions, quadrillions of T is equal to 0 compartment. Like it's even these numbers are very small, basically 10 to the power 10, like that. So the number of T is equal to 0 compartments which are there in each particle is huge. So the destruction which is happening in there is huge per Planck time. So every Planck time, so much destruction is happening. So so the Planck time has to be divided into that many number of parts. So every hop of the time resetting wave has to happen in that small fraction of time, which is basically several times faster than the speed of light. And that is the reason why I keep saying that the gravity related time resetting wave probably travels much faster than speed of light. Now, how much we need the model actually. Without that, we won't be able to tell exactly how much faster it will travel. But one thing is for sure that probably the how fast it travels depends basically on the mass. So the gravity of the sun will travel much faster than the gravity of the Earth, and the gravity of the central supermassive black hole of the Milky Way, which has several million solar masses of mass, then its gravity will travel much faster. So this is what is the prediction of DGR, which is not very exactly matching with instantaneous transmission of gravity with the Newton, but yes, it comes close. So force directed towards the Earth or object. So if there is an apple, there's a force which is directed downwards, which is pulling the apple down. That's what is the prediction of the Newtonian gravity. Now this force is given by the Newtonian formula. So our DGR predicts exactly the same thing, Like there is something called as a string of gravity. So as you can see the apple, and there is a zone right from apple to the Earth. All over that zone, there is an active spatial contraction happening because of gravitational time dilation. Or actually, it's the other way around. The active spatial contraction causes a secondary reduction in the velocity of the photons, which causes secondary time dilation. So the time dilation is actually not happening. It is only an illusionary time dilation. So that's what is the prediction of dynamic general relativity. So dynamic general relativity does say that there is a direct downwards directed force. So this here dynamic general relativity is coming in loggerheads with general relativity, which says that it is just the curvature of space-time. But basically the curvature, what exact curvature beneath the apple, it was not Einstein was not able to explain, but dynamic general relativity can explain it very nicely. The curvature is basically active spatial contraction, that is active loss of volume, which is directly proportional to the gravitational time dilation. So there is active loss of volume in the quantum form. So there is a force directed downwards from the object towards the Earth, or maybe from the Earth towards the sun. Now, in the last slide of this PPT, basically, I will be telling you how exactly the sun and the Earth, and how the active spatial contraction zones are basically distributed. So stay put till the end of the video, and I'll tell you. So yes, so Newtonian gravity is given by that formula. So which is basically proportional to mass, and it is inversely proportional to the radius. Gravity in DGR is actually absolutely agreeing to this. Absolutely, there is no question. It reduces proportional to the square of radius, and also it increases proportional to masses of both the gravitating objects. But there's an issue. Dynamic general relativity says that this kind of gravity happens only till gravitational limit. That is what? That is till gravitational time dilation is above Planck length, Planck time. So once gravitational time dilation caused by gravity of an object goes below Planck time, beyond that, there is no horizontal spatial contraction, but there's only a shifting of linear EPCs. It's just vertical shifting of EPCs, which are linear now. They are no longer curved EPCs. They become linear EPCs, and so they become curved EPCs. And these curved EPCs they become linear EPCs. So linear EPCs of one can join with the linear EPC of the other, and so on. So linear EPC is it very nicely explains why gravity shifts from Newtonian dynamics to a slightly modified dynamics. That is a MOND, that is a modified Newtonian dynamics. It very nicely explains why. Okay, so what are the predictions of general relativity and dynamic general relativity? So as I said, general relativity is actually exactly equivalent to dynamic general relativity at human scales, basically. So most of the predictions of general relativity can basically make much of sense in dynamic general relativity as well. So there is curved space-time even in DGR, but curved space-time is basically because of there is a change in geodesic basically because of dynamic general relativity, but that is because of EPCA formation, and that is because of active spatial contraction or active volume loss in the quantum form. So dynamic general relativity does show curved space-time. It can very nicely explain gravitational lensing because the shifting EPCAs, if the photon is coming in, the EPCA shift downwards, the photon will be pulled downwards. So it can very nicely explain gravitational lensing. It can nicely explain gravitational redshift because the space is itself moving. The EPCAs are being pulled downwards and inwards. So that causes the gravitational redshift. And also gravitational time dilation is very nicely explained in DGR. In fact, it is very it's very confusing in general relativity, but dynamic general relativity explains it very nicely with the active spatial contraction behind the photon clock, causing the photon clock to tick slower and causing the illusionary time dilation. So it predicts all the it goes very well with most of the predictions of general relativity. So dynamic general relativity has almost the same predictions as general relativity. So now in gravitational waves, there is a small difference. There are in gravity, general relativity, there is only one type of gravitational wave which travels with speed of light, and which is basically the one which causes the effect of gravity. But in dynamic general relativity, there are two types of gravitational waves. One is a time receding wave which travels very, very fast, much faster than speed of light. And the second one is, so this is a prediction of dynamic general relativity, that the time receding wave, or the wave which keeps resetting time, and the reaction time of the spatial EPCAs. So one EPCA contracts down, so the second EPCA reacts to it, then third reacts, then fourth reacts, then fifth reacts. So this reaction time, it has to be much faster than speed of light, and it doesn't violate general relativity because this is basically space which is contracting. So how fast space has to contract, or how there is no, so this is not a particle with mass, so there's no limit which the general relativity sets for how fast the space will contract. So this space is contracting very fast and it is reacting very fast. That is why the time receding wave is moving very rapidly. So the second type of gravitational wave is wherever there is potential energy. So if you are having a big ball, lead ball, and you are basically hanging it over the roof. So what is happening is that the ball is being pulled down. So there are EPCAs going all below the ball. They're pulling it, but there is a PC vacuum being created, but there is no compensation from the ball because the ball is not moving downwards. So there is a vacuum being created over here, PC vacuum. But that PC vacuum is not allowed. So from sides, there has to be compensation. So this compensation basically will move outwards with speed of light. So this is the gravitational wave, which is reason which is the one which is detected by LIGO. So this is what is the prediction of dynamic general relativity. So dynamic general relativity does predict two types of gravitational waves: the typical gravitational wave which we detected on LIGO, which travels with speed of light, is also predicted by DGR, and the other one is also predicted, which is the time resetting wave, which goes much faster than speed of light, almost instantaneous transfer of. So because within one Planck time, it can move several billion Planck lengths. So it's a very fast traveling time resetting wave. So gravitational interactions are much faster than speed of light. Okay, so there are some places where general relativity and dynamic general relativity come into loggerheads. So one of them is what? Gravitational time waves traveling with speed of light. DGR says otherwise. Prediction of dark matter explaining flat rotation curves. It doesn't need that. DGR doesn't need dark matter for the galaxy. Actually, it has dark matter candidate, but it doesn't need a dark matter candidate. But we have to be a bit cautious here, because we don't have mathematics yet, and we know that MOND, which is the thing which is which is what is very DGR is predicting that gravity behaves like MOND at long term scale. So MOND cannot by itself completely rule out dark matter for the galaxy clusters. So we have to be very cautious about it. But even if there is a dark matter like thing present, we have a dark matter candidate for it in DGR. So nothing to worry about in that sense. So that's what the prediction of dark matter is not needed, and flat rotation curves can be very easily explained with the help of linear EPCAs, and predicts existence of black holes. So black holes are there in DGR also. Black holes basically are a huge collection of t is equal to 0 compartments which are aggregated together, and they cause a lot of destruction. That's why they cause a lot of EPCA formation around them. So EPCA formation just within the event horizon of the black hole, the EPCAs are moving much faster than the speed of light. That is the reason why, because of the extreme amount of destruction, the inward movement of the EPCAs is faster than speed of light. That is the reason why no light can escape from that. So it can very nicely explain how is the curvature inside. It can also fortunately explain what is there at the center where there is singularity. GR general relativity predicts the singularity, where all the laws of physics break down. But DGR has no such singularity there. There are only t is equal to 0 compartments where destruction is happening. Now, so these singularities are not needed in DGR. So DGR, because DGR is a theory which is taken some assumptions from loop quantum gravity, which is basically limits infinities by limiting how small space-time can be. That's why the singularities is not a problem in DGR, but it's a problem with general relativity. So general relativity predicts that the c, or the speed of light, is constant, which is where DGR absolutely disagrees. DGR says that speed of light is variable because of the active spatial contraction. So this active spatial contraction is where DGR is basically different than general relativity. General relativity says that there is just a change in the shape or geodesic, but it's not active spatial contraction related change in the shape of the geodesic. So it doesn't tell in a quantum level what is happening and how exactly the volume is changing. Again, general relativity says that variability of time is absolute. So there is absolutely variable time. So there is no universal time in that. But in DGR, there are two types of time: absolute time and variable time. And the absolute time is the real time. The variable time is the illusionary time. So the variable time is variable because of the active spatial contraction or expansion. So this is another difference in DGR, that the expansion of the universe in DGR is because of negative energy, which is active creation rather than destruction. So over there, instead of gravitational time dilation, there will be gravitational time contraction. In general relativity, there's no such thing as time contraction or anything. This is a prediction which is actually used as prediction, because general relativity, you cannot really send an atomic clock in the intergalactic distance region and do an experiment to check whether it is ticking faster. This is a prediction of DGR, but it is unfortunately beyond testing. It's not testable. So what are the predictions of MOND versus DGR? So DGR says that beyond, so let's say the sun, basically. So the immediately around the sun, there will be EPCA formation, which are curved EPCAs. But as the time resisting wave goes further and further away, maybe half a light year or 1 light year or 2 light years or 3 light years away, the EPCA of the sun, instead of remaining curved, it becomes a linear EPCA. So EPCA is basically the eddy Planck compartment aggregate. So it's a Planck compartment aggregate, but it has become linear instead of curved. So if it is linear, then so in this particular area, gravity behaves slightly differently. Basically, gravity behaves. Gravity here is directly proportional not to the it's not related to one star or two stars. It's related to the entire mass of the galaxy. So the entire mass of the galaxy can put its influence here. So that is the reason why it is basically different here. Here the gravitational acceleration becomes constant. That's called as A naught. So because this linear EPCAs are just shifting, they're just shifting EPCAs. So this volume, there is one PC vacuum over here. So this PC vacuum is shifted to this here. So this PC vacuum is shifted to above, because there is a shift in the layers of eddy Planck compartment aggregates. So there's no horizontal volume contraction. So because there is no horizontal volume contraction, there is no, so the gravitational time dilation is below Planck length over here, below Planck times over here. And here the acceleration, instead of reducing, it becomes constant. So even after 1 light year, 2 light years, 3 light years, the same gravitational acceleration will be there, instead of becoming extremely small, and it keeps reducing as with reducing proportional to the radius. It won't reduce, it will keep. So that is why gravity over here is much stronger, and it is sort of agreeing with the Tully-Fisher relationship, basically because it agrees with MOND, basically. So agrees very well, very nicely with MOND, that the force reduces proportional to the radius rather than reducing proportional to the square of radius, and the gravitational acceleration becomes constant instead of reducing with distance. So this baryonic Tully-Fisher relationship, that is asymptotic velocity of is proportional to the fourth power of fourth, I'm sorry, this is a mistake actually. Fourth power of the velocity is proportional to the mass of the galaxy, basically. So there is an external field effect, which is also, which it is basically, so DGR says that even beyond the galaxy, there is linear EPCs keep going just even beyond the galaxy. So one galaxy can basically influence the other galaxy by linear EPCs. So the other galaxy can further influence the other. So that is why the intergalactic bonding is also with the help of a MOND rather than with Newtonian or Einsteinian type of gravity. So which means that here the gravity is much stronger than what is predicted by Newtonian gravity. So there is an external field effect over here, which is predicted by MOND, but it is not predicted by general relativity. So here it agrees pretty well with general relativity, because beyond galaxy also there will be linear EPCs. Linear EPCs will be there, which can so linear EPC of one galaxy can merge with the linear EPC of the other galaxy, with the third and with fourth. So like that. In fact, we'll come to that. But MOND is basically in DGR, these linear EPCs can have Mondian type forces from one corner of the universe to the other corner of the universe. So like that, one galaxy which is at the one corner of the universe, and it can affect the other galaxy which is at the different separate corner of the universe by Mondian gravity. So like that, that is the reason why there is something called as a Mondian gravity, which is affecting the entire, which is affecting two gravitating objects. Mondian gravity of the entire mass of the universe is basically pushing them apart. We'll come to that basically. So that is what was the prediction of Dirac's large number hypothesis. So yeah, prediction of entropic gravity versus DGR. Entropic gravity says that, now I don't know the exact details of mathematical details of entropic gravity as well, but it's basically saying that the gravity is an emergent phenomenon, and multiple small events happening together keep adding together, and then that is basically the manifested as gravity. So that way entropic gravity goes very well with DGR. Einstein's variable speed of light theory goes very well with DGR, because DGR is actually general relativity with a variable speed of light. But actually Einstein's VSL theory, Einstein did not realize why exactly this speed of light is variable in his theory. Basically, it's because of the active spatial contraction which is happening within, just behind the photon, which causes the hindering of the forward progression of the photon. So that way, dynamic general relativity can explain why speed of light is variable rather than constant. And so Dirac's large number hypothesis, basically it is a pretty big topic, and I don't want to go into controversy over here, but there are quite a few predictions of dynamic general relativity which match with Dirac's large number hypothesis. One of them is that G could probably be the Mondian type of gravity of the entire mass of the universe, which is basically pulling the two gravitating objects together. So what is G basically? G is a very small number. So this is a 10 to the power 10 or 10 to the power 8. So that much amount in the new denominator. So it's basically the existence of G is basically reducing the effective gravitational attraction of the two gravitating objects. So if there are two gravitating objects and they are basically attracting towards each other, so their masses will increase the gravitational attraction, and their distances will also, small distances, larger the distance is basically inversely proportional to the square of the radius. But basically, the existence of G is basically reducing the overall pull between the two gravitating objects. So this G could basically be Mondian gravity of the entire universe, which is acting on the two gravitating objects, pulling them apart. So it's basically anti-gravity effect of the Mondian gravity, which is okay with DGR. So DGR does predict that, and so it is at least a few of them are pretty much in line with DGR. So dynamic general relativity is in line with at least some predictions of the Dirac's large number hypothesis. Now there's something called as a scalar tensor vector gravity, or MOG, modified gravity. Now, before I wrote the book, I was having no idea what this is basically. But now I realize that this scalar tensor vector gravity is also pretty close to DGR basically, because the scalar tensor vector gravity, it proposes that nearer to the solar system, basically, if there are two gravitating objects, and there is a fifth force which is basically pulling them apart and hindering the gravity. That's the reason why the gravity here is weak. But as we go away at galactic levels, this particular hindrance is less, and that's why the gravity is much more stronger, which is very exactly what DGR is saying. DGR, what it's saying is that the entire mass of the universe and the center of the gravity galaxy, the entire mass of the universe is pulling the two gravitating objects apart, and that is causing the gravity to become weaker. But at the galactic level, the entire mass of the galaxy will basically send linear EPCs, and these linear EPCs will keep adding together. So if there are 100 million, 400 million stars, each of these stars will send linear EPCs at a point. So so the resultant force which happens at that point will be directly proportional to the mass of the galaxy rather than distance. So it won't have anything to do with the distance. So it's independent of distance. Actually, the gravitational acceleration is independent of distance. It is basically dependent only on the mass of the galaxy, which is very much in line with, I think, this scalar tensor vector gravity. There may be some differences. Basically, I'm not saying like that because I'm not aware of the complete theory and also mathematics part of it. So what are the predictions of quantum mechanics? So entanglement very nicely DGR nicely explains what exactly is entanglement. In fact, it's one of the assumptions of but basically the entanglement in DGR is different and entanglement in quantum mechanics is different. But entanglement of PCs is slightly different than entanglement of two particles. But the EPCAs which are formed because of active destruction which is happening in core of every particle can very nicely explain what is an entanglement of two PCs. And the faster than light travel of information in between two entangled particles is also very nicely explained by dynamic general relativity. Superposition is basically not needed for explanation in dynamic general relativity. Uncertainty principle and Pauli's exclusion principle are also pretty much consistent with dynamic general relativity. There is no problem with that. Now there are some, so Newton's laws. There are some things about Newton's laws like inertia, momentum, kinetic energy, potential energy. So these are actually very nicely explained by DGR. DGR goes to a pretty extreme extent, extreme details about how to understand inertia, why inertia happens, why momentum is there, where exactly does the kinetic energy lie, where does the potential energy lie. So that is why DGR is pretty well consistent with all of these, and in fact explains it in a very great detail. So that is why all these are okay. Wave particle duality of light and matter. They basically pop out of DGR without much effort. They're basically ingrained in that. So light, the wave of light is basically the wave front is basically the space-time changes in between the photons, and the photons basically are the packet of energy, which is basically the aggregates of t is equal to 0 compartments. That is there. This active there is active loss happening, and the this creating it creates EPCs which interact with other EPCs and time resetting waves basically, and then that there is a active spatial contraction. So here there's active spatial contraction, here also there's active spatial contraction. So the two active spatial contractions will merge and they'll interact. That is causing the entangle. That is basically the light wave which is predicted by DGR. So the DGR nicely, very in great detail, it can predict how the photon will look, how the wave front of light will look. That is the reason why DGR has, as I said, it can give predictions at very small levels, and it can give predictions at very large distances also. Electromagnetic force, bonding, chemistry, everything can be explained very nicely with DGR. So DGR has predictions about electromagnetism, and it is the electromagnetic force. One of the basic questions about bonding and chemistry, which is not known to the contemporary physics, and basically we are assuming that it is there, is that why there is an electron and there is a proton, or the nucleus. So why the electron doesn't keep going down, why it keeps falling, why it stops at the first atomic orbital? This question is addressed nowhere satisfactorily. So there are some vague answers, but there's no satisfactory explanation of this. The explanation with DGR is very simple actually. That the electron is here, the proton is here, and the electron has a multiple space-time changes all around it. So there are some space-time changes which are time dilation changes, and there are some space-time changes which are time contraction changes. There is active spatial expansion is happening around the electron, which we know obviously, because if two electrons are coming together, they repel each other. So there has to be somewhere there is active spatial expansion happening around the electron. So this active spatial expansion wave, it travels all around the nucleus, and it goes from here as well as goes from here, and it reaches each other, and they basically meet at the other end, which causes the electron from further moving downwards. So that's why electromagnetic bonding and electromagnetic force and chemistry, these are things which DGR can very nicely explain. Electricity, magnetism, radio waves, all of this can be very nicely explained in with DGR as well. So DGR basically goes very nicely with all of these theories without much effort. Thermodynamics, entropy, array of time. So all these things are very nicely explained by DGR. So how and why? So basically, presently, all these things are theoretical and basically phenomenological. So we have to test it whether the mathematics of it still works. But I don't think that mathematics should be much of a problem here. But still, it's still one step basically. So the first step is basically to form a good working model for DGR, which is actually consistent with all the mathematics, which is not yet done. Basically, only phenomenological description is there, The model is there, but the model requires a huge amount of computing, which presently I don't have. So it will need computing and all. So only after that we will be able to tell whether mathematically also DGR is consistent with all these theories. But I don't think that that will be that much of a problem. There are some hurdles in developing mathematics of DGR. We will come to that later. But so all these theories, which are seeing a very small part of the whole picture, are absolutely consistent with DGR. And that is the reason why all the predictions of all these theories are equivalent to predictions of DGR. So we have already tested basically so a single theory which is giving so many predictions which are correct, which is itself I would say it is a good thing for DGR. Basically, it's a highlight for DGR, or it's a win-win situation for DGR. But there are some which are, so there are some predictions which are almost the same with the general relativity and dynamic general relativity. And there are some predictions which are absolutely only given by dynamic general relativity. So these are the predictions which we have to look out for. Here, there is a prediction of, on the left side, what is the space-time changes around the Earth, which are predicted by general relativity, which is basically time dilation zones. So the time dilation zones which are predicted by, now this is a very, very hyper exaggerated figure. Don't worry about that. But the only thing is, the point is that space is not absolute in dynamic general relativity, in the general relativity of Einstein. So space is absolutely relative. So that is the reason why the time changes which are predicted by general relativity will have a very little, if at all. There will be definitely, even general relativity will predict that there is a small deviation. So there's something called as a preceding border and the receding border. So the Earth is basically traveling within the space. So so if the Earth is traveling in this direction, this is the preceding border, this is the receding border. So the Earth is traveling in one particular direction. We don't know that actually. It's a very complicated thing. But dynamic general relativity says that there's active destruction going on inside within every particle of the Earth, which means that so this destruction has to be compensated. So to compensate the destruction, EPCs are forming all around it. But as the Earth is moving from one point to other, the compensation is coming from the preceding border much more than the receding border. So there will be a very slight difference in the inward movement of the EPCs in the preceding border as compared to the receding border. Now this extra compensation which is happening in the preceding border, which is very slightly less in the receding border, probably is very, very small for very small particles. So this is basically true for any object, basically. So not only the Earth, but any small quantum object or photon or anything, everything will have this small change in the inward movement of the EPCs, which is basically the momentum. So even the Earth has a momentum, but the mass of the Earth is very huge. So the moment and the speed of the Earth is also very huge. So the momentum of the Earth is very huge. So this momentum is basically changes in the there is a slight asymmetry of the space-time around the Earth. So this momentum or this asymmetry is predicted by DGR. Now, this is basically a phenomenological description. So exact model, exact computer model, exact, we don't know yet. So this asymmetry will depend on the preceding and the receding border, which itself is a problem. So where exactly will the preceding border of the Earth lie and where exactly the receding border of the Earth will lie? There we will have to put drones and we have to put atomic clocks. We have to measure the preceding and the receding border time at various levels, and we have to measure the difference. But really, you know what? Definitely, this is a doable thing. Basically, it's not that it is definitely not that it needs a $1 billion investment or it needs a particle accelerator of the size of the Milky Way. No. So this is a doable experiment. So this is definitely doable. These are the predictions of DGR. So DGR is providing pretty good predictions. So now this is again another. So if you can see this is the last image which I said. So these are two gravitating bodies basically. So the DGR predicts that there will be a time receding wave which starts from here, and there will be time receding wave which starts from here. Both of them will meet together. They will combine together. So the time dilation. So this is basically what will be the prediction even of Einstein's general relativity. So there will be a zone in between where on this line where the gravitational time dilation which is caused by this keeps going down, but gravitational time dilation caused by this will keep. So basically the reduction of gravitational time dilation which is caused because of movement away from this particular body is basically compensated by the increase in the gravitational time dilation which is caused because of this. So basically what is happening is that in this particular line there will be it's like a string basically which has a extremely high amount of gravitational time dilation, and so if you see over here and here and here, the deviation of the gravitational time dilation will be much less, but the deviation over here there will be a gradient basically, but the gradient will be much less over here because there's a cancelling effect basically. So if as you go outwards, the gravitational time dilation of this particular thing will keep reducing, but the gravitational time dilation of this will keep on increasing. So as we are going towards it, so this compensation effect is there. So if you can understand that this is the Earth, this is the Sun, and this is the Earth, then there will be a difference in the gravitational time dilation here compared to here. So these are some predictions basically. So what is exactly happening is that there is a active spatial contraction right from here to here in this particular, and even in these places all over, all around, this layer, everywhere there will be active spatial contraction. So this layer will come down and will replace this layer. There will be a destruction over here. So this layer will go inside, and there will be this shifting of this layer inside. So this layer will shift inside. Like that, it will be all around. So there will be a actively contracting space all around the two particles, and there is an actively expanding space which will pull the will pull the two gravitating objects apart, which is basically the Mondian gravity of Mondian pull of the mass of the rest of the universe, which is basically the G. These are all the predictions of DGR. So DGR gives a lot of predictions actually. So all of them can be tested. So these are testable predictions. So you have to basically have multiple drones with atomic clocks all over here and all over here. and you can do that. It's so the same thing, actually, the same thing you can do with any heavenly body. So this you can do with Earth, and you can do with Sun also. So if you know the preceding and the receding border of the Sun, and you have multiple uh, satellites which are there on the preceding and the receding border, then you can find out that there is a difference in this time gradient. So here I will basically end it. There are quite a few other predictions of DGR which we will come to only afterward. But once we know the theory very nicely, only after you have read the book and all, which will take some time. So I recommend that you subscribe to this channel, and also uh, buy the book. The book will be available internationally very soon. I'm just waiting for that moment. So in the first introductory lecture, I have given my email ID where you can contact me if you want to, and you can follow me on Twitter. You can contact me or send a direct message on Twitter. And also, I believe that you subscribe and you share so that more and more number of people will be able to know what dynamic relativity is. And thank you very much for your attention. Thank you very much.